Hello everyone, welcome to the official YouTube channel of askIITians. I am Anik Ghosh with you. Welcome to the series of PBlock. In the last few classes, we have been going through the group 13 and the group 14, which is the grade 11 part of the PBlock. Now today we'll be starting with the grade 12 part of the PBlock, which is going to be starting from group 15. So group 15, 16, 17, 18, and these are the four groups that we are going to cover up in this part of series. Group 15 would be the biggest out of all these four. So definitely guys, I am trying to make two part of these videos of this group 15 video. What I meant to maintain here is 16, 17, 18 might be done in one part only, but group 15 might have two parts. In the first part today, we are gonna start with the nitrogens and mainly the basics of group 15 and the nitrogen series, nitrogen family in there, right? And in the second one, I'd be going for the phosphorus family. I mean, family means the phosphorus compounds, nitrogen compounds, right? Those who are here for the JEE means part only and not willing to go for the JEE Advanced for the time being, guys, you can just watch the first 30 minutes of the video and you will be able to get over with the JEE mains segment of group 15, right? Of a nitrogen family, I should rather say. But before we get started, just like every other video, guys, I'm going to mark the things up in the book first, what all things are there in your syllabus, and you have to go through. Okay, first, let me share my screen with you. As you can see that I have opened the part of group 15. Now we start from the, okay, as you can see the unit 7 is the P block elements, right? Here the P block elements are starting from group 13 to 18, but it is a grade 12. So we can understand it could be 15 to 18 here, right? Now, in our syllabus, the part which I'm marking, those are there in our syllabus. So starting with the occurrence, guys, mainly like I've been telling you in the other videos as well, we kind of neglect this part of occurrence, but we have to go through it for the JEE mains purposes. Okay. Then we have the properties, all the properties which are, you don't have to remember this table. Okay, I'm going to teach you whatever is important in here. The electronic configuration, atomic and ionic radii, ionization enthalpy, trends, electronegativity, physical properties, chemical properties. These are all there in our syllabus. Then after that, the anomalous property of nitrogen. This should be the last topic. So that gets over in here. Yeah, in here. So this is what you have in your syllabus of JEE mains, right? Till here, you have for group 15. Now, similarly, if you have to go to group 16, I guess you got my point here. This is nitrogen family. We're going to complete this today. Then we have the phosphorus family, phosphorus compounds. This I'm going to cover up in the next video. Okay, so just a second. Let's get loaded. Right. Now, group 16. Similar in group 16 as well, you have the occurrence. Then you have all the same things. You can see that electronic configuration, atomic and ionic radii, ionization enthalpy, electronic enthalpy, electronegativity. These are all the same like group 15. Similarly, all the way to the physical properties, chemical properties, anomalous behavior of oxygen. We have all these three in our syllabus. Anomalous behavior of oxygen till the anomalous behavior of oxygen is what there in our rationalized syllabus. So till here. Okay. Now you can check it up with your with the JEE syllabus. You'll be able to see they have mentioned these points only. So this is what you have to go through. Now, to be in the safer side, I'm gonna suggest you to go through a few more topics which can be clubbed with the syllabus. Okay, they can claim that although in the book it is outside of the syllabus marking, but still they can claim that this is within a syllabus topic. And now, how can they claim it? That is something I'm gonna tell you in the class. But what can they claim as within syllabus topic? They can claim these bonding structures are from the syllabus. See, try to understand my point here. Yeah, technically they are outside of our syllabus. Technically, in the NCRT, they are drawn outside of our syllabus, right? But there can be so many different ways through which they can claim that this is a part of syllabus only. Okay, now how can they do that? Let's say, see, I'm just considering all the possibilities those are there, all the scenarios those are there. As we are going through this chapter, let's not take any more risks. See, these bondings are actually a part of chemical bonding chapter, right? You can find out all this bonding with the help of chemical bonding. Then the angle, then the resonating structure. These are the topics they can anytime include, and they can ask you these kind of questions from there. So they won't even claim that this is from the P block. They would claim that this is from the chemical bonding chapter. So for that reason, guys, let's be in the safer side. Let's go through all the structures once. These are not at all difficult. I'm going to give you a lot of shortcuts for that. But remember this, for every single P block chapter, we need to go through every single bonding related questions. That means how do they look like? Just make sure that you can draw their structures. You know how do they look like. Okay, that's all. Other than that, you'd be always safe. There'd be no other question that they can ask you. The chemical, these kind of chemical reaction type questions, they cannot ask you. Now, those who are there, those who are here for JEE Advanced, for them, guys, my notes would be sufficient, right? I guess you have been going for group 13, group 14 with me here. Yeah, so group 15, my notes would be sufficient, but you can clearly understand, guys, this is inorganic chemistry, right? There is nothing, you can understand that they cannot create a new question. All they can do is they can mix and merge with the same concepts that you already know, correct? And they do that actually. All right, so I would suggest all of you to go through the JEE Advanced PYQs. You'll be able to see that whatever I'll be teaching you in these notes, in this YouTube videos, you'll be able to see that every single question would be covered in here, right? But yes, guys, be ready for the surprises for JEE Advanced. So I would suggest you to go through. There is a book called JD Lee, right? So go through that book if you want to study this chapter from a book for JEE Advanced. Otherwise, for JEE Mains, only your NCERT is more than sufficient, and my notes are also more than sufficient for you. Okay. Now let's get started with this. So first, guys, we are going to go for the occurrence. In this part, the occurrence is very, very important. Let's call it group 15 here. So, guys, as you can see, the group 15 elements, they are found in many, many places, right? Group 15 elements are also called the chalcogens. Why do we call them the chalcogens? Because they are the ones, those who are choking, right? Specifically, nitrogen is a choking element. As nitrogen is choking element, as a result, we call them the family of choking elements, right? So as a result, we call them the chalcogens. Chalcogens means choking elements. So wherever you have nitrogen, you kind of choke there. Now, what is the occurrence of this elements over here, mainly the group 15 elements? So if you are talking about nitrogen and phosphorus, the nitrogen is a very, very, abundant in the nature as gas, nitrogen gas, 74%. But those nitrogens are not usable. So from where do we get the usable amount of nitrogen? That we get from the earth crust as chili saltpeter. We call them chili saltpeter because this kind of NaNO3 compound, this compound is found in Chile, right? In the country Chile. That's why we call them chili saltpeter. So the chili saltpeter, it's a source of nitrogen, which is NaNO3. Similarly, we have another source which is called the Indian saltpeter, which is potassium nitrate. The sodium nitrate is chili saltpeter, and potassium nitrate is the Indian saltpeter. These are the two sources from the earth crust for nitrogen. Similarly, for phosphorus, what are the sources that we have? Fluoroapatite, very, very important compound, guys. Very, very important compound. This is there in our enamel as well, in our teeth, in our enamel. This compound is also found in there. So, as you can see, Ca9PO4 whole 6 dot Ca2, right? So this is the compound fluoroapatite. It's the main component of phosphate rocks. So the phosphate rocks, which are made up of fluoroapatite, that particular material is actually our source of phosphorus. Why are we just leaning onto nitrogen and phosphorus? Because the rest of them are found in the earth very easily. They are very, very abundant. You can know, you know that arsenic, antimony, bismuth, they are found as, bismuth is a metal anyway, right? Arsenic is a metal. So their abundance is very, very fine. As you can see, arsenic, antimony, bismuth are mainly found in sulfide ores. Otherwise, like bismuth, metals, they have a high abundance always, right? Basically, nitrogen and phosphorus is what are important for us, right? Now, there are some points that I have written over here. This I am gonna discuss about in detail. That ionization energy 2 of bismuth is greater than antimony, and antimony and bismuth has same electronegativity. You just note it down. I'm going to come to these two topics, but these are the two statements I want you to know, and I want you to try to figure out the reason till I say the reason. Okay, bismuth ionization energy 2 is greater than ionization energy 3 of antimony. Do you understand that? That is ionization energy 3 and ionization energy 2 of bismuth. These are what we're comparing here. But that's 2, we see that bismuth is winning. So what is the reason behind it? You think about this question. And antimony and bismuth has same electronegativity. How is that possible? When we are moving from antimony to bismuth, the electronegativity should decrease. How is this the same? So that is what we are gonna talk about going forward. Okay, if you see the values are here, guys, these are I'm mentioning, I'm trying to highlight these few topics points in here, because when they ask you, the trends are there in our syllabus. Let's say they ask you the electronegativity trend of group 15. What you went like is the general trend nitrogen, phosphorus, arsenic, antimony, bismuth, but that would be wrong because antimony and bismuth would be having same electronegativity. So you should know these values, right? Now, this part I'll be covering up in the chemical properties. Right now, we are going to go for the physical properties first. So in the physical properties means, guys, we talk about boiling point, we talk about melting point, we talk about solubility, these kind of. All the elements of this group are polyatomic. That's a very good thing that all of them, all the compounds or elements over here, they combine, they have the property of catenation, right? Like N2 is a gas, but the others are solid. So they are polyatomic, but out of them, only N2 is the gas. Whereas P4, phosphorus, is a solid, right? Arsenic, it's a metal, like metalloid, but you're going towards metal, so they are going to be solid anyway. But nitrogen is only gas, the rest of them are solids. That means what really is happening, guys? Nitrogen is gas, going down, they are all solid. What do they mean by that? That means the boiling point is increasing. More you go down, the boiling point is increasing, but it's not that simple. If you notice what I've written over here, the boiling point is increasing from top to bottom, but the melting point increases still arsenic, but decreases in antimony and bismuth. Very, very important point, guys. Boiling point is increasing from top to bottom. What is boiling point? Boiling point is solid turning into, liquid turning into gas or vapor. This is increasing. Why is it increasing? Because the molecular weight is increasing from top to bottom. If the top to bottom molecular weight increases, then definitely boiling point would increase. That is not even a point of discussion. But what has happened to melting point? Guys, melting point is the conversion of solid to liquid. So there is one thing that you have to consider here when you do the melting point conversion. It's about the strength of the solid. It's about the packing of the solid. Now, packing of a solid depends on packing efficiency. Packing efficiency. Now, what is this packing efficiency? See, there can be so many parameters that can decide the packing efficiency. It can be the number of unpaired electrons. It can be the symmetrical arrangement. It can be so many things really here. Now, what are they saying? Melting point is increasing till arsenic. Melting point should increase all the way till bismuth actually. But we saw that, let's say this is our nitrogen, this is our phosphorus, this is our arsenic, this is our antimony, this is our bismuth. This is our melting point. So we saw that the melting point is increasing till arsenic. Then again, antimony, bismuth, their melting point decreases. Okay, why is this happening? That's the question here now. Why suddenly it is like it's not directly going up? It should go up directly. But what happened to the antimony and the bismuth? Why is the melting point so low? Now here's the reason. This happens due to the inert pair effect. Do you remember this, guys? IPE, inert pair effect. Okay, in the last two videos, we have been talking about inert pair effects very, very often, right? Group 13, group 14, and group 15. These three elements, these three groups. The last element of this group is thallium, lead, and bismuth. These three elements, they show two less valency than the group valency. Group valency means group 13, so group valency should be 3. Group 14, so group valency should be 4. Group 15, so group valency should be 5. But they have 2 less than that, always. Valency is 2 less than that. The thallium's valence has been found to be plus 1, and lead is plus 2, and bismuth is more famous as plus 3. This is inert pair effect. Now, because of this inert pair effect, what is happening is as the s electrons are not participating in the metal-metal bonding. There we go. So the packing efficiency is low. Why is it low? Because the electrons are not participating in bonding and the interaction decreases, so that's the boiling point. So till arsenic everything was going fine. After arsenic onwards, what we see is the metal-metal bonding is not really working that easily, okay, because of the inert pair effect. So s electrons are not participating in the metal-metal bonding. There is no such bonds to make. As a result, we see that the interaction decreases, so the boiling point decreases. So this is a very, very important information. Going to the next one, which is the electronic configuration. As you can see, for all of them, as they are group 16, so their electronic configuration would always be NH2 NP. NH2 NP4 is the electronic configuration for all of them. That's a randomly we choose bismuth 5s2 5s4. This is the electronic configuration of any element present in group 15. Now we go for the atomic and the ionic radius. Okay. Now again, because of, okay, now we go to the first question that I asked you, that why bismuth and antimony has the same electronegativity. So here the answer is inert pair effect. The reason is inert pair effect here. Why do they have same electronegativity? They should have different electronegativity, but because of the bismuth is having inert pair effect, as a result, the Z star, the effective nuclear charge for bismuth is powerful, it's more. As a result, it becomes inert pair, they become inert. Okay. Okay. Now, what is happening to the atomic radius? As you can see, as we move on, the atomic radius is increasing. So according to that, bismuth would be having highest, then antimony, then arsenic. This should be the order for atomic radius. Order for atomic radius. Okay, but there is one thing that you need to notice, that when we are moving from nitrogen to phosphorus, okay, wait a second. This should be the right answer. Okay, now you can see that when you are moving from nitrogen to phosphorus, the jump is pretty high, isn't it? But if you notice for the next one, phosphorus to arsenic, the jump is pretty much low, not as much as nitrogen to phosphorus. That too is because of the contractions, decontraction specifically. Okay. Now let's go for ionization energy. Look at the values in here once. It is going to show a normal trend. 1402, 1012, 947, and 834, 700. Okay. So this shows the proper general order only. So we see that the order is going like, just a second. The order would be going like, first would be bismuth. No, wait, ionization energy, na? First would be your nitrogen. Achha, even if we do not have these values, then also we know, right? When we move from top to bottom, the electronegativity decreases. So nitrogen, phosphorus, arsenic, antimony. This should be the original order of ionization energy. Okay. Let's move on to the electronegativity. Electronegativity, for example, we know that it is because of the electron dragging tendency. It is the tendency to drag the electron towards themselves, right? That is called the electronegativity. Now, if you notice the values one more time, electronegativity value is 3.05, 2.05, 2.2, 1.8, 165. Okay. So these are the 1.65, sorry. So these are the values of electronegativity. Here also you can see that from nitrogen has the highest electronegativity. After that, you have the highest value as 2.2, which is arsenic. After arsenic, we have 2.05, which is phosphorus. After arsenic, we have phosphorus. Then we have 1.8, which is antimony. Then we have bismuth. So this is the electronegativity order. Now, if you're wondering why is arsenic coming before this phosphorus, this is happening because of d and m block contraction. Okay, so because of the D and A block interaction, the arsenic, the phosphorus, it is much, what should I say? If I talk about phosphorus, because of the D and A block contraction, you'll be able to see the electronegativity value for them is comparatively higher for phosphorus, right? As a result, I mean, sorry, for arsenic. As a result, what actually happens over here, what I meant to say is, for arsenic, because of the D and F contraction, specifically D contraction, the size goes down, so electronegativity would go up, right? So in that way, we can consider this. Okay, now let's go to the chemical property. Under the chemical property section, the first question goes like, N shows all types of oxidation states. So these are the oxidation state that you can see. Acha, quickly pause this video and figure out the oxidation state of nitrogen in every single case. Quickly, oxidation state of nitrogen in every single cases. What would be the oxidation state of nitrogen? Quickly solve this. Okay, so I believe all of you have done it. Now, if I try to find out the oxidation state of all the nitrogens over here, starting with this would be -3. This should be -2. This should be minus +2, -2, -1. Correct? Check it, guys, whether it's matching with your answer or not. This should be 0. This should be 2, 2 plus 1. This should be +2. So these are the values that you're supposed to get from here, right? Now, what you see, guys, we have the oxidation state starting from -3 all the way to +2. So for this n block, for this nitrogen, the values, it can go all the way to +2. And again, this is not the end. We can go even beyond that. If you see, if I draw a compound which goes like in the green color, let's say +2, you can see, right? Let's draw +3 then, right? N2O3, then N2O4, then N2O5. So till +5, like here it is +3, here it is +4, here it would be +5. But till +5, starting from -3 till +5, these many variation of oxidation state can be shown by nitrogen. Now, this carries a little bit of misunderstanding here, guys. Oxidation state and the valencies are not the same thing. So, it is oxidation state, not valency. See, oxidation state is a terminology which is only applicable. It's an arbitrary thing. Oxidation state doesn't even exist in the real life, right? It's a terminology which only is applicable if and only if your compound can be broken into ionic method, anionic method, I should rather say. So these are all covalent compounds. We cannot break them into ionic method, right? But if we could break them as an ionic compound, then it would have been achieving that particular charge on the top of their head. So that's why this is an arbitrary value. So +5 can be achieved by oxidation number method, by oxidation state method for nitrogen, but that is not the valency. Valency for nitrogen can go up to +4. Okay, not +5. Now, the stability of +5 oxidation state decreases down the group. Okay, in group 15, in the chalcogens, which all elements do I have? We have, I mean, in the nitrogen. All right, one second. Have I called them chalcogen in the beginning? Or we should call it the nicogen or nictogen. Chalcogens is the group 16, right? Nictogens or nicogens, same. Okay, chalcogens are the salt forming compounds. Salt forming compounds means oxygen. Group 16 are called chalcogens. Okay, they make salts, right? They are formed, not salt form. Salt forming is halogens. Salt forming is called halogen compounds. So those who are forming salt. Group 16 are called chalcogens because we get them from their copper ores. Yes, that is why we call them chalcogens, right? Now, the stability of +5 oxidation state decreases down the group. If I talk about the nitrogen compounds, what are the compounds which are there? Nitrogen, phosphorus, arsenic, antimony, bismuth. They're saying that the +5 oxidation state, the stability of +5 oxidation state. So nitrogen can show +5, but down the group, more you go down the group, the +5 oxidation state is very, very rare. Now, why is that? Because, guys, I believe you know that these are group 15 that we are talking about. Before that, I had group 14, and before that, I have group 13. Guys, in all these three groups, thallium, lead, these compounds are there, and these thallium, lead, and bismuth, these three are the element those who can show this inert pair effect. Correct? So bismuth is more stable at plus 3 oxidation state. That's why when you go down the group, plus 5 oxidation state decreases. So phosphorus can also show plus 5. Arsenic can also show plus 5. But from antimony onwards, you start seeing plus 3 as plus 5 as well. But for bismuth, it is only plus 3 that we get to see. Now, we are going to write the answer in this way, that because of inert pair effect, bismuth shows plus 3 oxidation state only, whereas antimony is capable of showing plus 3 as well as plus 5. So that's why we can conclude that more you go down the group, because of inert pair effect, because of the contractions, the plus 5 oxygen state is decreasing. Because, guys, you cannot lose 5 electrons anymore, because the electrons are under much higher effective nuclear charge, much higher Z star present in it, right? Now, moving on to the next one. The next question goes like, NCl5 and NF5 doesn't exist. They do not exist. Guys, I told you this before as well, that plus 5 oxidation state is a separate thing, plus 5 valency is a separate thing. If I talk about nitrogen electronic configuration, it goes like 1s2, 2s2, 2p3. Correct? That it is, if it is correct, then you can clearly see nitrogen's valency is only 3. Correct? The number of unpaired electrons are the valencies according to the VBT. So the valency is only 3. So nitrogen with NCl5 is not possible, because here the valencies are going all the way to plus 5. But what about phosphorus? Can phosphorus make PCl5? The answer is yes. How? Because if for phosphorus, if I see, the electronic configuration is 3s2, 3p3. Correct? Argon 3s2, 3p3. Now, in 3, there is a 3d as well. In 2, there is no such 2d, but in 3, there is a 3d. As a result, what actually happens is, let's say this is phosphorus's electronic configuration. Right now, this is also 3, so it can make PCl3 as well. But in the excited state, this is ground state phosphorus. But if I take it to the excited state, because of the d orbital, the electron jumps in there. As a result, the electronic configuration looks like this. Guys, always remember, when you're trying to make covalent bonds, there, the number of unpaired electrons is the valency. As you can see, how many unpaired electrons are there? That is 5 now. Earlier, that was 3. So here, phosphorus can make PCl5 as well as PCl3 depending on which state of phosphorus you are using. If you're using ground state phosphorus, then PCl3. If you're using excited state phosphorus, then you can get the PCl5 as well. How can you excite an element? How can you say, sir, how I want a PCl5, not a PCl3? What should I have to do for this? Increase the amount of chlorine in the reaction medium when phosphorus and chlorine are reacted together, and make the phosphorus a little bit high energetic. Means just give it a little bit of energy. Specifically, guys, if you use the allotrope of phosphoruses, there are 3 types of phosphoruses out there: white phosphorus, red phosphorus, and black phosphorus. White phosphorus among them is the most reactive. So by using white phosphorus also, you can get PCl3, PCl5. Red phosphorus, I guess you have heard about this, guys, in Hell-Bollard-Zelensky reaction. Red phosphorus, HI, right? That's the same thing. So it's the red phosphorus with an allotrope of phosphorus, which is comparatively a little less reactive than the white phosphorus. Okay. Now coming to the last part, which is for the JEE main students, anomalous property of nitrogen. Guys, every single element, every single group's first element is anomalous, right? Because of the same reasons. One is the smaller size. But guys, as they have a smaller size, that leads to a high ionization energy, which is my third point. The ionization energy is always high. They seem to act like an inert element, because see, if you need a lot of energy to take out the electrons, to react, then you are actually inert in nature, right? So that's why nitrogen acts like an inert element for all of them. They act like inert element. High electronegativity. This is also an eventual thing, guys. If you're small in size, your electronegativity has to be really, very, very high. Now, because they are high, what we are gonna see here, because the electronegativity is high, we're gonna see a lot of things happening. If I talk about group 15 nitrogen, guys, you're gonna see hydrogen bonding happening. This hydrogen bonding is there in group 16 first element, which is oxygen, and group 17 first element, which is fluorine as well, correct? So this is going to be a common thing for all three of them because of the high electronegativity that they have. No d orbital. We have just seen that because of their unavailability of d orbital, their valency cannot be expanded. Guys, for every other people, the valencies can be expanded. Phosphorus, the valency can be 3 and 5. Arsenic also, antimony also. But for nitrogen, it can be only 3. But guys, if they ask you what is the highest valency of nitrogen, you are going to be answering it as 4. How? Because if I talk about ammonia, it can react with another molecule to make ammonium, NH4 plus. So the highest valency of nitrogen is 4, not 3. 3 is the covalency. Fourth one is coordinate covalency. Okay, like that. Now, let's see what are anomalous properties. Because of these reasons, what are anomalous properties do we see for nitrogen? First, why nitrogen forms 3 bonds in its molecular state, whereas phosphorus, arsenic, and antimony makes a single bond? Very, very important question. This question comes very often. Why do nitrogen form 3 bonds in the molecular state? What do I mean by that? What I mean is nitrogen makes a triple bond N. But for phosphorus, they do not make multiple bonds actually. They make single bonds between them. This is phosphorus. This is nitrogen. So the question is, why do nitrogen form 3 bonds, whereas phosphorus, arsenic, antimony make single bond? The answer is very simple. It's about the bond strength. The answer is bond strength. So as you can see, when we are bonding between two nitrogens, this bond is formed by 2p overlap. When we are talking about phosphorus bonding, this is 3p overlap. Then arsenic bonding is 4p overlap. So you can understand, if I move from 2p overlap to 4p overlap to 5p overlap, you can understand the overlapping would be going down, the energy of overlap would be going down, the overlapping won't be good enough. When it is 2p overlap, the atoms are very small and their overlapping is going to be stronger. So for NN bond, the bond strength is strong bonds due to better overlapping. So as guys, nitrogen bonds are stronger due to better overlapping. That's why they go for second bond and third bond. Try to understand this point, guys. Let's say you are trying to do a business, trying to make a startup. Say you want to run a company. So in there, you'll be bonding with those people where your connectivity is better, with whom your understanding is better. If with a dealer, your understanding is better, you're gonna make multiple deals with that guy. Similarly, the nitrogen bonds are going for multiple bonding formation because of the better overlapping, because of the stronger bond formation, right? Whereas phosphorus, arsenic bonds are not at all strong like nitrogen bonds are with respect to overlapping. That's why, guys, we see single bonds for everybody else. For nitrogen, we see triple bond present. Because of this reason, guys, nitrogen acts like an inert gas as well. Because do you understand, 3 bonds is what you have to break in order to make a compound of nitrogen, which asks for a huge amount of energy. That part is gonna come going forward. But now, a very, very controversial question. Why is NN bond is weaker than PP bond? Try to understand this point now. They are saying that in triple bond makes it a stronger compound than P4. Why is that? N2 is stronger than P4. Why is that? Because N triple bond is being formed. So this is fine. Molecular wise, fine. But they are comparing now one NN bond versus one PP bond. Now they're saying, other than overlap, put aside the overlapping segment. Now you tell me which bond is stronger. Is it N1 NN sigma bond is stronger, or is it PP sigma bond who is stronger? The answer is PP sigma bond is stronger than NN sigma bond. Forget about overlapping for the time being, guys. Overlapping creates multiple bond formation. Okay, but now even with a good overlap, still we have found that in single bond is for some other reason it's not strong enough, not as much as we expected. What is the logic behind it? So in single bond is weaker than PP single bond. This is the question. Now why is that happening? This is the same reason, guys, why F2 is weaker than Cl2. Same question. FF bond is weaker than ClCl bond. Same reason. What is the reason? Because of the lone pair repulsion. Do you know what do we call it? We call it the alpha effect. This alpha effect. This is not in your syllabus, guys. Okay, we call it the alpha effect because if a nitrogen side by side they have two lone pairs present in them, as a result these lone pairs of electrons are repelling each other, right? Interelectronic repulsion. Because of this interelectronic repulsion, the bond, although the overlap is high, still the bond has been found to be weaker. Now you might say, sir, in phosphorus also you have lone pair. But guys, the phosphorus bond is longer in size because of the size, because of the, I mean, longer in length because of the size of phosphorus. As they are longer, the distance is higher. So the interelectron repulsion is not working for phosphorus. That is one reason. Second reason is because of the presence of d orbital. So one is the distance. First reason is the distance. The second reason is the presence of d orbital. Guys, when you have a d orbital, that means you have a vacant room in your apartment. That means the lone pair, they are not forced to be in the top of phosphorus. If they feel any repulsion or anything, they kind of get delocalized in the d orbital which they have, which is open, which is vacant. So they kind of they have a room to get stabilized by that repulsion, from that repulsion, by getting spreaded in the d orbital. So because of these two reasons, we can consider that PP bond is comparatively stronger. Same question comes for fluorine and chlorine as well, guys. Bond dissociation energy of fluorine is higher than fluorine because of the same reason, okay? Now, going to the third question. Why the trihalides except BF3 are predominantly covalent in nature? Guys, there is something that I need to tell you. See, for bismuth, the oxidation state should be +3 because of the inner pair effect. This is something that I told you in the beginning. But there is one compound that can form +5 also. That is BiF5. Remember this compound. BiF5 is the only compound. It's the only compound with +5 oxidation state of bismuth. Only compound, right? Now, why the trihalides except BiF3 are predominantly covalent in nature? Guys, let's consider PCl3 for an example, PCl5 for an. Now, what are they saying? Why the trihalides are predominantly covalent in nature? Just a second. +3, +5. Just a second. Why the trihalides except BiF3? Okay, are predominantly covalent in nature. There are multiple ways to answer this question actually. I'm trying to find out the easiest of them actually here. So you can understand it this way. So as you can see the charges on the top of phosphorus in both the cases. Right. You can see that for PCl3 it is +3, for PCl5 it is +5. right? So if the charges are high, then you can clearly understand the bond would be more and more ionic. If the charges are low, then the bond would be more and more covalent, correct? So in that way, you can consider that this would be covalent in nature. But there is one conflict which is coming here in this question. Okay. Guys, I need to recheck this question because I believe there is something wrong about this question. All these questions are coming from PYQ though, but still I feel like there is something wrong about it. Why the trihalides are predominantly covalent in nature? It should be the pentahalide which should be predominantly covalent in nature. Let's keep it for later for the time being. Okay, I'm gonna check this question up one more time. Okay. Anyway, let's just skip this part for a second, and we're gonna come back into this question by the end of this video only. Okay. Let's moving on to the next one, which is nitrogen cannot form p pi d pi bonding, but phosphorus can form R3p double bonded. This is important now, guys. Okay. See, what is p pi d pi bonding? If you have watched my group 13 videos, you know what it is already. For those who haven't watched it yet, guys, first you go through the group 13 video. Because in group 13, I have actually covered up all the conceptual things which are there in the entire group chemistry. Okay. So what is the p pi d pi bonding? So let's say there are two elements A and B. They're making a pi. Now say element A is using its p orbital and the element B is using its d orbital to make this pi. If they do that, then we call it a p pi d pi. If both of them are using the p orbitals to make this pi bond, that is p pi p pi. Example of p pi is guys, come on, try it one. What is an example of p pi bonding? Where the pi bonding has been formed by the p orbital of both the elements. The answer is oxygen. In oxygen, both the O atoms are using the p orbitals to make the double bond of oxygen, correct? Now, let's talk about R3PO for a second. Let's talk about this compound. This compound has already made 1, 2, 3, 4 bonds. 1, 2, 3, 4 sigma bonds. It has already made 4 sigma. Now the fifth bond is the pi, correct? That means it is making 5 bonds. That means phosphorus is in excited state because only in excited state it can have pi unpaired electrons. So let's draw the excited state configuration then. That's correct. Now have a look. I'm drawing this bond, sigma bond with R. I'm drawing this bond now, sigma bond with another R. I'm drawing this bond now, sigma bond with another R. I'm drawing this bond now, sigma bond with another oxygen. Then I'm drawing this bond, which is a pi bond with another oxygen, correct? So now, if you are wondering that, sir, why are you drawing the pi bond in the end? Because guys, that's how it is, right? You make the sigma bond first, then the pi bond. Always that is how the bonding happens. Now, if you notice in this part, the pi bond is being formed by the d orbital of the phosphorus, correct? That means in order to make a p pi d pi bonding, as a p pi is oxygen and the d orbital is for phosphorus. You need to have a d orbital in order to make a p pi d pi bonding. For nitrogen, electronic configuration is 2s2, 2p6, 2p3. So it doesn't even have a d orbital to make a p pi d pi. So that's why nitrogen cannot make p pi d pi bonding. So what kind of bonding can nitrogen make then? Let's say we talk about this compound. In here, what kind of bonding is nitrogen making this pi bond? It is a p pi p pi. Nitrogen is also using its p orbital. Oxygen is also using its p orbital to make this pi. That's why we call it a p pi p pi. Okay. Now, if you want to learn more about this p pi p pi and p pi d pi bonding, that you can find in my group 13 videos. Okay. The reactivity with hydrides. Now, guys, when we talk about the reactivity of hydride systems, so first of all, you understand that why do we call it hydride? Hydride means H minus. Okay, hydride means H minus. Now let's say we talk about the hydrides of group 15. So they are ammonia, phosphine, arsine, and you have stilbene hydrides, which is antimony hydrides, and then we have bismuth hydrides. For antimony and bismuth, we call it bismuth hydride and antimony hydride because, guys, they are metallic in nature. Now, their reactivity is in this order. So we see that more we move from bismuth to nitrogen, the reactivity is decreasing. Now, why is that? This question can also be framed in this manner that this is their reducing power. This is their reducing power. The reducing power of bismuth is higher than nitrogen. The same thing. Because, guys, reduction or reaction means bond breaking and bond making. When we talk about that Bi and hydrogen bond, hydrogen is using its 1s orbital, whereas Bi is using its 2p, 5p orbitals. Whereas nitrogen over here is using its 2p orbital, and hydrogen over here is using its 1s orbital. So here you can see that the huge orbital mismatching is happening here. If there is an orbital mismatch, then there is a weak bonding. If there is a weak bond, then there is a bond cleavage. Very easily, this bond breaks. As this bond breaks, they are very good proton donor or H plus donor, or you can consider they are very good reducing agent, or you can consider that they are very, very reactive in nature. Any way you want to put it, right? But the answer is with respect to the orbital mismatch. Now, let's talk about the bond angles here. Now, when you talk about bond angles for nitrogen, phosphorus, arsenic, antimony, and bismuth, you have this as the angle, are the angles given here. If you have made it so far in the video, that means, guys, you are either targeting for JEE Advanced or you are finding this video a little bit interesting. You're able to understand it. Now, even if you're targeting for JEE Mains, and if you have made it so far of the video, I'm going to tell you, you are gathering out very, very important information here. Every single question that I am mentioning right now, these are the only kind of question that they ask you. Yeah, they can frame it in different manner, but that's all they can ask you, right? So make sure every single question that I'm showing in this video, you are noting it down, and you are then right after this video is over, you are reading it from the NCERT at least once. Okay. Now, coming to the next point, guys, which is a very, very, very important point of this chapter, also for chemical bonding chapters, which is known as the Drago's rule. This is called the Drago's rule. Ammonia, phosphine, arsine, stilbene hydrides, and bismuth hydride, they are the ones those who follow Drago's rule. Now, what is the Drago's rule? Drago's rule says that for nitrogen, ammonia, the hybridization is sp3. Right? We know that for a fact that nitrogen is sp3 hybridized. How do we do this? So for nitrogen, you know there is a lone pair and there are 3 hydrogens present in it. Now, that means 3 sigma bonds and 1 lone pair, adding up to 4. 4 means hybridization is sp3. So for ammonia, it is sp3 hybridized. That's why the bond angle should be 109 degree. But now the problem is nitrogen has a lone pair. So according to the BSEPR theory of grade 11, you can clearly understand the bond angles are challenged by the lone pair bond pair repulsion. This repulsion is called lone pair bond pair repulsion. Because of the lone pair bond pair repulsion, the value has gone down a little bit and it is now as 107. This is fine. This is understandable and everything is fine. When we go to phosphorus, what is happening for phosphorus now? You see, for phosphorus, the value is found to be 93. Arsenic, 91. Antimony, 91. And bismuth, it is 90. Looking at these values, what Drago said is, that this much of huge deviation from 109 degree is not normal. They said that these compounds are unhybridized compounds. They said that these are unhybridized compounds. So let's say if somebody asks you what is the hybridization of ammonia, you are going to go like nitrogen is sp3. But if they ask the same question for phosphorus, you have to call it that it is an unhybridized compound. It doesn't have any hybridization. Now, how does that make sense? See, if it is unhybridized compounds, then how much sense does that make? If the hydrogens make bonding with these three pure p orbitals, then let's say this is your px, this is your py, this is your pz. If the hydrogens are making bonding with the pure p orbital, then this is how they are going to look like. This is how they are going to look like. What would be the angle between them, px and py? It is 90 degrees. And you see the value close to 90 degrees. So he went like, these values are showing that their values are very, very close to 90 degree instead of 109 degree. So actually for phosphorus, arsenic, antimony, and bismuth, they are not even hybridized compound. They're rather, we should call them an unhybridized compound. They are using the pure p orbitals actually. They're not using hybridized sp3 or sp2 orbitals. So as a result, these are called Drago compounds. And are these are the only Drago compounds those are there? No guys, this is also there in group 16 as well. Water is sp3, but everybody else after water are unhybridized. This is how it works. This Draco's rule is a very, very famous thing that they love to ask. Okay, moving into the next one now. Reactivity towards oxygen. The order of acidic character of oxides goes in this order. This is a very simple question because, guys, figure out the oxidation numbers in all the cases. This would be your +1, this is +2, this is +3, this is +4, this is +5. So more you are moving from +1 oxidation state to +5 oxidation state, your Z star is increasing, right? Why is the Z star increasing? Because +5 to +1 to +5 means you are taking out the electrons, right? So Z star is increasing. If the Z star is increasing, now nitrogen in +1 taking an electron, and if I consider nitrogen is in +5 taking an electron, which one would be easier? Definitely this guy would be taking more electrons. So that's why we know that electrons acceptors, they are treated as Lewis acids. Electron acceptors are treated as Lewis acids. So from there, guys, we can conclude that from nitrogen +1 to +5, Lewis acidity increases. Lewis acidity increases. That's why the acidic character is highest in N2O. N2O and NO are neutral species. Okay? That is a small thing that you should be knowing in here. If the amount of oxygen versus the amount of other element which is there, that is less than equals to 1.5, that is less than equals to 1.5, then they turn out to be neutral, which you can see for the case of NO and N2O. Just a second. Less than equals to 1. Less than equals to 1. Then in that case, we found them neutral, right? As a result, we can see that N2 and NO are actually neutral in nature. Generally, from N2O3 onwards, the acidity starts going up. Now, going to the next one, which is reactivity or the order of acidity. Acidity, guys, you can clearly understand it's the same thing, which is like I have just told you that when the oxidation number is increasing, that time the acidity is also increasing. Other than that, we also know that metallic oxides are generally basic in nature, and non-metallic oxides are acidic in nature. Non-metallic oxides They are actually acidic in nature. This part also I have discussed properly in the group 13 video. Now, as you see that nitrogen 2 antimony 2 bismuth, the metallic character is increasing, right? It's becoming more and more metallic in here. Becoming more and more metallic. If the metallic character is increasing, then oxides basicity will decrease. Oxides basicity is increasing. Because you can clearly understand, let's say we are talking about Na2O. You know, it's a metallic oxide, right? When you dissolve it in water, you get NaOH. So metallic oxides are basic in nature. That's why this is basic. More you go down the group towards being more metallic, that is more basic as well in nature. Now, the reaction towards halogen. Why nitrogen is unable to form pentahalides although it has oxidation state of +5? Like I said, oxidation state are not equals to valence. Valency is the number of unpaired electrons. An oxidation state is the charge on the atom if they are broken. Charge on the atom if they are broken as ionic compound. As ionic compounds. Then the charge that we find, that is, so arbitrarily it can go to +5, but in reality it cannot go to +5 in oxidation number in valence method. Okay. pH 3 has a lower boiling point than ammonia. Now it's a fairly good question. If you see, when you go down the group from nitrogen to phosphorus to arsenic to antimony, when you go down the group, the size increases. That means the van der Waals forces are increasing. That means the boiling point should increase. This much is fine. But now if you notice, what are they saying? That means if I have ammonia versus phosphine, then pH 3 boiling point should be greater than NH3, isn't it? Right? But NH3 is greater than pH 3. Now why is that? The answer is because of hydrogen bond. You know, nitrogen is capable of making 4 hydrogen bonding, which nobody else can do, right? It can make a hydrogen bonding from this center, and from this center. From this center. Okay? Because of hydrogen bonding, you can say that ammonia has a higher boiling. See, I told you, the previous question was wrong. Why the pentahalides are more covalent than trihalides? Now this is the right question. I guess I have written the wrong question earlier. Okay. Now, let's say I have PCl3 and I have PCl5. Now it would make sense. For PCl3 it is +3, PCl5 it is +5. Right? More positive charge. If I have more positive charge, then we can say more Z star. The effective nuclear charge will also be high. The same thing. Positive charge is coming from nucleus only. More Z star leads to more polarizing power. More polarizing power, right? If I have a +5 oxidation state, he can polarize the electron cloud of the covalent compounds very easily. If they have more polarizing power, then more covalence in nature. That's how we can conclude. So more plus charge means more covalent because they have more Z star values. They are more covalent in nature. This is how you can conclude this. Now, why bismuth is the strongest reducing agent amongst all the hydrogen of group? So I've just shown you when we go for bismuth, in the Bi hydrogen bond, bismuth is using 5p orbital and hydrogen is using 1p orbital. So this bismuth hydrogen bond that you see over here, that is very, very weak. So as a result, BiH3 is a very good, very strong reducing agent because they can break this bond. Let's talk about the properties of nitrogen. Now, guys, the preparation reactions are really, really important. Beyond this, if you're a JEE main student, you don't have to go beyond this point. Beyond this point, JEE Advanced students also are there. You're going to stick around. JEE main students, you can skip to the next video. Okay. Now, properties of nitrogen. First, guys, how do we form nitrogen? NH4NO2, ammonium nitrite. It's a very, very important reagent. Nitrite. What actually happens is when you're reacting ammonium chloride with sodium nitrite, you get ammonium nitrite. And ammonium nitrite from here, if you take out water, 2 molecules of water, 2 molecules of water means you can see 4 hydrogen and 2 oxygen. So from NH4NO2, you take out 4 hydrogen and 2 oxygen. Then what would it become? 4 hydrogens are gone, 2 oxygens are gone. It would become N2 now. This is how you can get by just heating ammonium nitrate. Okay. The next method of preparation is very, very important. It's called the chemical volcanic. It's called the chemical volcanic. Now, what happens over here? If you have ammonium dichromate, what happens is if you heat it, you will be getting nitrogen gas, water, and chromic oxide, the green colored chromic oxide. For that, we are going to watch a small video over here for better understanding of this. So, let's watch this video now.
How to make volcano-like chemical reaction using ammonium dichromate. For this experiment we'll need ammonium dichromate and lighter. Okay, let's pour chemical on this tray. Just trying to make like a little hill like that. Now I'm gonna set this thing on fire.
Okay, before we get into it, guys, I guess you have been there with me in the coordination chemistry videos, as well as in DNA block series. There, guys, I have told you plenty amount of times that this dichromate series in here, the color is coming from the ligand to metal charge transfer. So be it potassium dichromate, be it ammonium dichromate, be it sodium dichromate, it would always be orange. Not because of the sodium, potassium, or ammonium. It is because of the dichromate. Dichromate is always going to be orange in color because the oxygen to chromium, the ligand to metal charge transfer is happening over there. Here also you can see it is orange.
See what happens. Don't try this at home, guys. It didn't work first time, it was probably not enough fire. sound. Let's do it again.
So guys, as you can see over here, I don't know whether you can see it properly or not, but this ash is not gray. It is actually greenish in color. Okay, just pay attention. Try to look through if you can see the color. It is actually deep. The deep green color, actually it's chromic oxide. And why do you see this volcano kind of texture? It is because of that nitrogen gas is coming. So nitrogen gas is inflammable, as you can see over here. Because of that, this volcano texture is coming. And if you see over here, although it is really, really very difficult to understand, but it is actually a green colored ash. It's not really, that ash color. It's not that. I guess this view is a little bit. Just think about a very, very deep green color. Okay, that is what this color is all about. Now I guess you can see it, right? Or still it looks like gray only, isn't it? Look in here actually. Look in this part, right? Here, part of it. It looks green, isn't it? It's actually green in color. That's all about this video. So now this thing that you have found over there, that is your chromic oxide. So this is a green colored ash. And the nitrogen, it goes out as a volcano, right? This is the preparation reaction. Okay. Barium nitride, guys, any kind of nitride, if you heat it, it can be barium, it can be calcium, anything, any metal nitride. If you heat it, you get nitrogen gas out. Okay. Sodium nitride, as you can see, if it is calcium, then also it's the same thing. If you heat it, you get nitrogen. These are simple. Now, let's go for the next thing, which is it is very, very difficult to break in triple bond N, but lithium magnesium, being very electropositive, can break it. Okay, so this part is important for us. It is very difficult to break in triple bond N for sure. You have to break 3 bonds in here. Definitely, it's going to be very, very difficult. And I told you nitrogen acts like an inert gas. You know, guys, even in the packet of chips, you have nitrogen gas filled in it, right? Because it acts like an inert gas. If you do not have, let's say, I'm going to tell you, when we used to work on a lab, let's say we do not have argon or helium or those kind of inert gas in our lab, and we want to make a reaction in inert atmosphere. Let's say I don't want oxygen to be around in my atmosphere when I want to do the reaction, just to avoid oxidation. So in that cases, guys, we take a box and we fill it up with nitrogen gas. Actually, the purpose is the same actually, because nitrogen is acting like an inert gas, because none of the elements generally react with nitrogen, but who does? Lithium and magnesium. These two compounds, they do react with nitrogen. So if you now notice, where are they situated? If I talk about group 1 and group 2, lithium is the first element of group 1. Forget about hydrogen from there. So Li, Na, K, Ruby, these are the things. And for group 2, beryllium and magnesium. From this periodic property chapter, guys, you know there is something called diagonal relationship, right? So lithium and magnesium, whatever properties lithium can show, magnesium can show the similar kind of property. See, the amount of energy, let's say we call it bond dissociation energy. It is a very, very high value for nitrogen gas. The bond dissociation energy is very, very high. But this high bond dissociation energy of nitrogen can be compensated by the lattice enthalpy of Li3. This Li3L is highly negative. It is highly negative. Why is it highly negative, guys? Because lithium being a very, very strongly electropositive element, the lattice enthalpy for lithium is so negative that the high bond dissociation energy needed to break the bond is being compensated. Bond dissociation energy is positive. Let's say it is positive 600. The lattice enthalpy we find minus, let's say 1200 or something in that range. So as a result, it is always being compensated. Other than lithium and magnesium, guys, there are not many elements those who are capable of surpassing this particular high bond dissociation energy of nitrogen, and that's why they doesn't even exist. You know, guys, for a reason, for the fact that whenever you are trying to make a compound, your lattice enthalpy has to be more, like compensation has to be more than the cost, right? So that's why lithium and magnesium can make it happen. Now we look into some compounds of ammonia, guys. So we start with, I mean, nitrogen. We start with the compound ammonia here. First, how do we make ammonia? As you can see, NH4Cl plus a base. So guys, these methods are really, really important, whichever things that I've written in here. The ammonium chloride and base, you can understand, guys, ammonium chloride is actually a salt, right? Salt of ammonia and hydrogen chloride. If you react it with a base, what would happen? It's just a kind of a double displacement reaction, guys. Calcium with chlorine, they react together to make CaCl2. And then from ammonia, the hydrogen and the OH, they react together to make water, and the ammonia is, in this way, we can get ammonia. There's another way, as you can see, ammonium sulfate, when it's treated with base, it's the same thing, guys. Here it is a salt of hydrogen chloride and ammonia, and here is the salt of sulfuric acid and ammonia. The same thing, you get ammonia, H2SO4, same thing. Okay, very, very simple. Now, this process is important, Haber's process. Haber's process of ammonia formation is very simple, and N2 plus 3H2 is 2NH3. Here, guys, we use iron as a catalyst and molybdenum as a promoter for this process. Okay. Now, why does ammonia act like a Lewis base? All right, guys, you know that Lewis bases are another way we call them the ligands, or we can also call them a nucleophile. So you know for a fact that when as ammonia has a lone pair, it acts like a neutral nucleophile. It can donate its lone pair to attach with a Lewis acid. Let's go for an example. Let's say ammonia is being reacted with a BCl3. BCl3 has a vacant orbital. Ammonia has a filled lone pair. So they go for a coordinate covalent compound, adapt. So here we form this BCl3 plus minus. This coordination chemistry is being formed. Here, this is a Lewis base. This is a Lewis acid. Now, in coordination compound, we know that ammonia is also acting like a borderline ligand, and there ammonia can form coordination complexes with several different metals. For copper, we are drawing this CuNH3 whole 4, this compound, plus, right? So these kind of compounds we always see, right? This is blue in color. I hope you know this from coordination chemistry. This is bluish in color. So that's how, when they ask you this question, do give them some examples of it. But yeah, luckily they're never gonna ask you this question in boards. So yeah, it's just a fact that you need to. Now, the other compound is nitric acid. Guys, in nitric acid, this brown ring test is really, really important. In analytical chemistry, in our classes, you have seen the brown ring test already. So this part would be a little bit easier for you. Acha, how do we form this nitric acid here? It's very simple method is there, which is NaNO3 plus H2SO4 double displacement reaction, Na2SO4 plus HNO3. But this process is not at all important. The important process is the Ostwald's process. See, for every single mineral acid, there is a different process of making it. For H2SO4, we call it the contact process. For HNO3, we call it the Ostwald's process. So the process is very simple. What we first do is we take ammonia, then we oxidize it. If I oxidize or burn ammonia, I either get NO or we can get NO2. Let's consider that we got nitric oxide. Okay, by the way, platinum rhodium catalyst is being used. This is a very, very important point. They ask you which particular compound is being used in Oswald's process. This particular question can be coming from D and F block as well. As you can see, platinum and rhodium are D and F block compounds. So in the D and F block chapter, if you go to the catalytic property segment, there you'll be able to see this question is there, like where do they act like this catalyst, the DNA block. So there we have this Haber's process, we have contact process, we have Oswald's process. It is written in there. Now, in the Oswald's process, the first step, burning of ammonia is actually where platinum and rhodium is being given. So we get nitric oxide from there, but we need nitrogen dioxide. So we further burn it to get the nitrogen dioxide. Nitrogen dioxide, when it is reacted with water, when it is mixed with water, you get nitric acid, 68%. Now, why 68%? Because the rest of the 32% is water, because I mixed it in water. So we need a dehydrating agent to take out the water. So we use concentrated H2SO4 as a dehydrating agent to take out the water from HNO3. And as a result, your HNO3 gets pure, which is purified, which is 98. So this Oswald's process is the process that we use in industry. Now, this particular reaction is very, very important for your JEE Advanced, and this question comes very often as well. When we react metals with nitric acid. Now, guys, there's a shortcut that I made for this particular topic. As you can see, what I have wanted, what I have gone through it, what I have made over here is on reacting with a metal, when we reacted with dilute nitric acid. Guys, you know, nitric acid is actually an oxidizing agent, correct? So it breaks into H2O plus NO2 plus nascent oxygen. When you have, let's call it like this, NXOY plus. See, nitrogen have many kinds of oxides. NO2, N2, NO, N2O3, N2O5, many of them. There can be one of these oxides getting formed over here. Now, which oxide would get formed? That depends on what kind of nitric acid you have. If you have dilute nitric acid, then the supply of oxygen is limited. Then you get NO or N2. As you can see here, the nitrogen is to oxygen is 1:1 or 2:1. So here oxygen is less, nitrogen is more, correct? But when you have concentrated nitric acid, there it is 1:2. The amount of oxygen is more. Why? Because definitely it's an oxidizing agent. Now more oxygen is being formed, right? This oxygen is called nascent oxygen. Nascent oxygen means newborn oxygen as well. Newborn oxygen, very, very reactive state. Okay. Let's say they say that what would happen when copper is reacted with dilute agents? Copper nitrate, so everybody can. This is going to happen because it's a copper nitrate, it's a displacement reaction. But with that, which oxide of nitrogen is going to get formed? Guys, it is dilute. So either NO or N2O. As you can see, for copper, it is NO from dilute oxide and H2. So this is fine then, as the oxygen, as the dilute HNO3 is being given. So NO. If I give concentrated HNO3, then what will be the oxide? NO2. Rest of them are constant. Now go for the zinc. For zinc, when it is reacting with HNO3, what we get is zinc nitrate, and as it is diluted, so we get either NO or N2O. And here we can get N2O, as you can see. In copper, it was NO. For zinc, it is N2. This much, guys, you try to remember. After that, with concentrated, we again got NO. So every single time you have concentrated, it would be NO2. Dilute, it can be N2O or NO. Metal to metal, that can vary. For copper, it is NO. For zinc, it is, that's all. Okay. This question comes very often. On Browning complex, I believe, guys, this is something I taught you already in the analytical chemistry. As you can see, when you have a nitrate, for that identification test of nitrate, ID test of nitrate is bounding test, correct? So when you have nitrate salt, you react it with Fe2 plus, which is FeSO4 generally, freshly prepared ferrous sulfate, and in presence of concentrated H2SO4, what would happen? You have performed this in the lab, right? What we find is, we find this penta-aqua nitrosoferrate compound, right? Penta-aqua nitrosoferrate compound. Now, This particular compound that we have found in here, guys, this is called the brown ring complex because you get the brown ring in here. And the special fact about this is this brown ring has iron in +1 oxidation state because this NO is NO plus. This part is being very well discussed in the qualitative analysis classes, guys. That iron over here, generally iron has only +2 or +3 oxidation state, but here NO is actually nitrosonium NO plus. NO can act like two types, NO plus and NO minus. Here it is NO plus. As a result, we get iron as +1. Then again, guys, in the qualitative analysis class, I've also taught you about nitroprusside. In nitroprusside also there is an NO present in it, right? Sodium nitroprusside in there for sulfide test. So that in nitroprusside complex NO is also NO plus, right? This is what we have discussed. So guys, we're going to keep it up to this for this video. In the next video, we are going to start with phosphorus and the phosphorus compounds. This part is going to be not much present in it. But as we are going to go through the bonding and stuff in here, so that might take a little while. But other than that, guys, there is nothing much in it. All the conceptual part is over. In the next part of this video, we are going to go for the phosphorus. Okay, so we are going to keep it up to this for this video. Make sure that you have subscribed to the channel, guys, and you are also watching every single part of these videos. Don't watch a particular video directly starting from nowhere. That is never going to help you, because your target over here is not to complete your syllabus, guys. Your target over here to understand the thing, right? Make sure that you have gone through the topics that I have marked in the book if you are a JEE main sample. You have to read it line by line for PBlock, guys, because they can ask you any kind of question, any absurd kind of question in this year examination, because you can clearly understand the syllabus has been rationalized. So they are going to search for the tricks. They are going to search for the very small minute details in the book. So make sure you are reading from the NCERT and NCERT only. For those who are targeting for JEE Advanced, as I suggested, guys, you try to have the JD Lee book, or otherwise my notes would be enough as well. All right, so let's keep it up to this for this video. We are gonna meet each other in the next video, Group 15 Part 1. Goodbye, everyone.